Hey students, Friday here. For our next plate of lunch, we will be exploring the final way that chunks of crust can interact with each other, side by side. What happens when these giant pieces of land build up pressure? How do we measure that? The chunks of crust are called plates, and where two plates meet, it's called a plate boundary. Our final boundary that we're going to discuss is called transform boundaries, and these boundaries are very different than the other two boundaries that we discussed, in that the first two boundaries we discussed, convergent boundaries and divergent boundaries, are slow-moving boundaries that take thousands or tens of thousands or hundreds of thousands of years to move significant distances. A transform plate boundary is different in that these are fast boundaries. They can happen in a very short period of time. There's an easy way for us to model the nature of this. If you hold your hands together so that they are flat, palm to palm, and start shaking your hands is representing building up pressure between those two boundaries. And then when you slide your two palms side to side in relation to each other, that slipping pattern is what would release energy in what we call commonly an earthquake. And so it's easy here in the United States to think of a place where a transform plate boundary occurs where there are lots and lots of earthquakes. That would be the San Andreas Fault in California. Now there can be earthquakes at any plate boundary. Convergent boundaries can have earthquakes, divergent boundaries can have earthquakes, and transform boundaries can have earthquakes. In fact, when we get to our next course dinner, you will have an opportunity to explore how different plate boundaries produce different earthquakes and what we have learned from that. What we want to focus on during the rest of this video is that since transform boundaries produce a lot of earthquakes, we want to learn a little bit about what earthquakes are, where they occur, and how do scientists go about measuring the nature of earthquakes. Let's, before we continue on, see a visual of what transform boundaries look like so that you can get it within your headspace. So back to this same model as before. At a transform boundary, there is motion from side to side along these plates, but I want to point out that there is a limitation to this model. This model seems to indicate that this is a gradual, continual motion of these plates. I think that this model could do a better job of showing this what it really is, which would be that the model wouldn't move for a period of time, and then suddenly those two arrows would move directly in relation to each other very, very quickly. I'll show you some pictures of what this looks like in real life in a little bit. Got to make sure I'm in the right file. There it is. Found it. Thanks for your patience. So, earthquakes are happening when there is this very rapid shift between two plates that are grinding past each other. They build up pressure, and then they release that pressure. And we have names for the locations both where that pressure is released underneath the ground and where it is felt on the surface. And here are two images that should help you to think about what the difference is between these two things. The focus of an earthquake is where the actual release of pressure is under the ground. So you can see in this three-dimensional diagram, we have the focus here represented by the star, and the epicenter of the earthquake is the point directly above it on the ground where the earthquake would be felt the strongest. Here's a side-to-side diagram where once again you can see the focus where the fault is between these two pieces of crust where they're sliding past each other, one going to the left, one going to the right, and the epicenter directly above it is where the earthquake would be felt the strongest. You've probably heard of a scale that is frequently used in the news to describe the intensity of earthquakes, and it is the wrong scale. We do not use this scale anymore. But since sometimes people, when they're in school, rely upon whatever they learn in school or whatever they hear of, they use old terminology. So there was this gentleman named Charles Richter who came up with a first scale for earthquakes. This is the older scale. You've probably heard of a Richter scale in relation to earthquakes. It's no longer used used because the Richter scale was based mostly upon motion of the ground. And as we've learned how to analyze earthquakes more over time, we've realized that just measuring ground movement is not the only way to understand the amount of energy that is released in the release of pressure in an earthquake. The Richter scale is really bad at accurately measuring and helping us to understand the energy released in really big earthquakes. So instead, we use a scale called the moment magnitude scale. Frequently, geologists will report things to reporters in the moment magnitude scale, and then the reporters will report it as the Richter scale. And so there's always we can always be better at communicating with the news media so that they can report things accurately. The moment magnitude scale is the current scale that geologists use. It's a lot more accurate because it's based upon a lot more variables. It's not only based upon ground movement and how much the earth moves, but it's also related to a measurement of how earthquake waves move differently through different types of rocks based upon their rigidity. In other words, the more info that you can include as part of a measurement, the more accurate and precise your measurements will be. The Richter scale is not very precise for very major earthquakes. And so here's a comparison that you can see comparing what a value was on the Richter scale compared to the moment magnitude scale. And sometimes it's close, but if you look at this example where the arrow is located, the Richter scale has sometimes rated earthquakes at a 6.4, where based upon the rigidity of rock, it's actually much more severe than what the Richter scale originally described. And they can go the other way as well. Whoops, I accidentally rotated this image. That was fun. Woo! I'll write it. Oh, it's almost as if a mini earthquake is affecting our image. It can go the other way too. In this example down here, we have the Richter scale rating a earthquake as much more significant than it was based upon the moment magnitude scale. So when we include more information in our measurements are more accurate. So here's an example of comparing the destructive energy of earthquakes at different times of Earth's history related to different events. And so on the left-hand side of the diagram, we have the magnitude of the earthquake in the moment magnitude scale, and we have the amount of energy released. And it's important to note that whether we're talking about the Richter scale or the moment magnitude scale, these are logarithmic scales, meaning that every time that you go up a number on the scale, an earthquake is 10 times more powerful. So a magnitude 2 earthquake, when you go to magnitude 3, the magnitude 3 is 10 times more powerful. If you go from a 2 to a 4 earthquake, that's 100 times more powerful. 2 to 5, 1,000 times more powerful. 2 to 6, 10,000 times more powerful. Now, what this central portion of the diagram shows is the number of earthquakes worldwide that meet each of the different magnitudes, so that you can see that there are far fewer earthquakes that happen at higher magnitudes every year compared to earthquakes of lower magnitude. The Chile earthquake of 1960, considering one of the most devastating earthquakes because many people were killed in this earthquake in Chile, South America, was a very strong earthquake, nearing 10 on the moment magnitude scale. The Japanese earthquake of 2011, which I'll talk about during our dinner section of our experience with earth science. We call it the Fukushima earthquake of 2011. I'll explain a little bit about the significance of that earthquake. And so the San Francisco 1906 earthquake, which due to gas pipes being used for electric lighting, produced all sorts of gas fires, and San Francisco burned to the ground in 1906 as a result of the effects of this earthquake. Your parent or guardian might remember the 1989 earthquake in Loma Prieta, California, which happened during the World Series, a moment magnitude 7 earthquake. And so we use these scales to help us to think about these different earthquakes. Now let's talk a little bit about the technology that is used to detect earthquakes. The technology used to detect earthquakes is called a seismometer. You may have seen it with the thing with the little needle on it, where depending upon how crazy the needle gets, that can indicate the strength of the earthquake. Seism refers to shake. Ometer refers to something that measures something. So a seismometer is an instrument that we use to measure shaking. That's not the same thing, but is related to a seismograph. A seismograph is the depiction of the shaking with the little needle drawing on the paper. So that's the basics of how we measure these different things. We'll talk a little bit more about how we use our understanding of waves as physicists to understand what's happening, but before we get there at a later time, let's talk a little bit about some significant pictures here that can show us what happened. So here we have somebody standing in between two pieces of fence where the ground where he's standing actually shifted, and this entire section of fence became offset from this section of fence. Here's another one where railroad tracks have been bent tremendously as a result of a seismic shift at a transformed plate boundary. You may have heard a couple years ago that we had a major earthquake in Oklahoma that we actually felt here in Nebraska. This happened 2 years ago in 2016 around September, Labor Day, and it was really cool at the time for school purpose because we were thinking about these things, and over the weekend we had an earthquake that we felt here in Nebraska. The earthquake likely happened right here where this red dot is located. It was 5.6 on the moment magnitude scale, pretty significant. And one thing that's important for us to note over the last couple of years since they changed the laws for how you can dig and search for natural resources in Oklahoma, there has been an explosion of earthquakes in Oklahoma and the surrounding area. Why? Well, that's due to something that we call hydraulic fracturing or fracking. That's when you pump water and other chemicals under the ground to try to deliberately break rock to release natural gas. And as geologists, we're really worried about this because when you deliberately break rock, well, that's what produces earthquakes. Breaking rock can produce earthquakes. So we've had this explosion of earthquakes in the Midwest happening, especially around Oklahoma, where the laws changed, basically allowing unrestricted fracking in the area. Those chemicals can in turn potentially contaminate groundwater as well. And so it's something as scientists that we're really monitoring to try to understand better to protect people. Why did we feel that earthquake in Omaha? Well, check out this image. This is an underground rock formation called the Humboldt Fault Zone, and one of the types of rock that is present in that region is called the Nemaha Ridge. The Nemaha Ridge rocks behave differently and have a different rigidity than the other rocks in the area, and notice where this Nemaha Ridge goes. Directly from northern Oklahoma, directly towards near where Omaha is located. So this earthquake wave basically traveled up this Nemaha Ridge, and part of the reason why we were able to feel it in Omaha, despite the fact that it was over 500 miles away, is because this earthquake wave was able to travel much more easily up this Nemaha Ridge for us to be able to understand it. Now, we're fracking in a wide variety of different locations throughout the United States. Why are we doing this? Well, the red areas here represent shale gas. We're trying to get burnable gas out of the ground to replace burnable coal. We're basically running out of inexpensive ways to mine coal, and as a result of that, fracturing or breaking of rock is a way for us to get gas that we can burn in our homes to, heat during the winter. There's definitely an ethical dilemma present here. We want people to be able to have heat during the winter, but at the same time, we want to be stewards of our environment and help to prevent people from being affected by earthquakes that they don't need to have. If you want to read more about this, why fracking is a concern, you can go to this article from CNN that talks a little bit about the earthquakes in Oklahoma due to the oil and gas industry. Thanks for watching. I hope this was able to help you get some of your answers for some of the basic questions about how people are affected by earthquakes and how we measure them. Be sure to answer the questions on the back page to summarize your understanding before moving on to the next section. Thanks for watching.